In this single phase transformer, the turn ratio is given as 1 by 100. The primary to secondary turn ratio is 1 by 100. In the secondary, a resistance and a capacitance are connected. The value of resistance is 80 kilo ohm and the capacitive reactance is 40 kilo ohm. So in this transformer we have to find out the RMS value of this current I. So to find out this current, we will refer all the elements of the secondary side to the primary side. So while referring, these two winding will be diminished and this R will be R dash will be R into 1 by 100 whole square, 1 by 100 whole square. So R dash will be 80 into 10 to power 3 divided by 10 to power 4. This will be 8 ohm. Similarly, XC dash will be, this will be 4 ohm. Okay. Or if we write in proper form, XC dash will be, this is only magnitude of reactance, with phasor reactance will be minus J4. So now the circuit diagram will be inductive reactance J10 ohm, then resistance R dash, this is 8 ohm, and capacitive reactance minus J4 ohm. Okay, J10 minus J4, this will be J6. So overall impedance will be 8 plus J6. So the magnitude of impedance will be 10 ohm root under 8 square plus 6 square. This voltage is 100 RMS. So RMS current will be RMS voltage divided by magnitude of Z. This is 100 divided by 10 ampere. The direction of rotation of single phase capacitor and induction motor is reversed by, there are 4 options given to reverse the direction of rotation of capacitor and induction motor. The first option says interchanging the terminal of AC supply. In induction motor, there is one main winding, let's say this is main winding and this is auxiliary winding, main winding and auxiliary winding. Okay, so in capacitor and induction motor, or in induction motor, we have studied that the direction of rotation can be changed by either by interchanging the connection of main winding or by interchanging the connection of auxiliary winding. Okay, and both the windings are connected to same AC supply. Let's say this is AC supply. So both the windings are connected to same AC supply. Let's say these are connected in this way. Okay, so if you will reverse the AC supply for both the winding, the connection will be interchanged. Okay, to reverse the direction of rotation of induction motor, only the connection of only one winding has to be interchanged. If you will interchange the connection of both the windings, the direction of rotation will not be reversed. You have to change, or you have to interchange the connection of only one winding. So if the connection of AC supply is interchanged, means this is connected to here and this part is connected to the upper side of source. Okay, this way connection of both the windings will be interchanged and the direction of rotation of induction motor will not be reversed. So this option is wrong. By interchanging the terminal of capacitor, if you will change the terminal of capacitor, it will not make any difference. Let's say in AC circuit, in induction motor, capacitor is connected to produce phase difference between the current of main winding and auxiliary winding. The purpose is capacitor is to produce phase difference between current of main winding and auxiliary winding. So let's say this is an AC circuit. If you will reverse the connection, if you will interchange the plate of capacitor, this is, let's say this is 1, this is 2. In the other case, you interchange the orientation of capacitor. Let's say this is second plate and this is first plate. The overall phase difference of the circuit will not change. It will not make any difference. Okay, so by doing this, the direction of rotation cannot be reversed. The C option says interchanging the terminal of auxiliary winding. It means you are interchanging the terminal of only one winding. So in this way, the direction of rotation can be reversed. This option is correct. Interchanging the terminal of both the winding. Okay, the meaning of this statement is same as the meaning of a statement in option 1. If you will interchange the terminal of AC supply, the terminal of both the windings will be interchanged, and in this case the direction of rotation will not be reversed. This option is wrong. Even if the connections are not interchanged, if the position of main winding and auxiliary winding will be interchanged, in this case also the direction may be reversed. So these things we have already discussed in the theory lecture. The direction can be reversed by, this can also be reversed by interchanging the position of main winding and auxiliary winding. The flux linkage lambda and current I relation for an electromagnetic system is lambda is equal to root under I divided by G, where G is air gap length. Lambda is given as the total flux linkage lambda divided by G, where G is air gap length. When I is equal to 2 ampere and G is equal to 10 centimeter, the magnitude of mechanical force on the moving part in Newton is, we have to find out the magnitude of mechanical force on the moving part. Just to take an example, let me draw a diagram. Let's say this is a core and a winding is wound on this core. This is a voltage source. This is also a core. Okay. So due to current in this winding, MMF will be there, and due to MMF there will be a flux, and the flux will take this path. Okay, because in this path, this way only, the line of flux will face minimum air gap. This is the air gap length G. Okay. Now the flux has tendency to reduce the reluctance of the path in which flux is set up. Okay, and we know that the reluctance of air gap is very high. Reluctance of air gap is much greater than reluctance of core. So in this path, in this region, reluctance is very low, and here it will face very high reluctance. Okay, so it has a tendency to reduce the reluctance. And how reluctance will be reduced? The total reluctance, if this is also a core, okay, if this core will move towards the, if this core will move towards this setup. Okay, so there will be a force on this bar, on this material, such that the overall reluctance of the path is reduced. Okay, so this length is given as g. This will be variable. So to solve it, I will assume this as x. This is variable length x. And the total flux linkage, there will be flux, and the total flux linkage will be n into phi. This is given as lambda. So lambda is related as lambda is equal to root under I divided by g. In general, in transformer or in simple system, we have studied that L is total flux linkage is equal to L into I, where L is a constant. L is inductance of the system. But here, if this bar will move towards this direction, the reluctance will be variable. So inductance will also be a variable. So the total flux linkage need not be directly proportional to I. So whatever is the relation, this relation is given. And now we have to find out the force acting on this bar. The formula for force is d by dx of the stored energy in the field, and which is a function of total flux linkage and position x. The magnitude of force is given by this formula, where W field is the stored energy in the magnetic field. In simple system, what we have studied, the stored energy in an inductance is half Li square, or this can be written as Li whole square divided by L, or half, this is lambda square by L, where L is constant. But in this case, to find out the total stored energy, we will use this formula. This is integration from 0 to psi. When this bar was at infinity, there will be no stored energy. Okay, so we have to find out the total stored energy when this bar moves from infinity to this position. So when the bar was at infinity, the total flux linkage was 0, and when this bar is at this position, let's say it has the total flux linkage psi. So we'll integrate it from 0 to psi, and the elemental change in stored energy is I d psi. This will be I into d psi. The total stored energy is integration elemental stored energy, and elemental stored energy is I d psi, where I is also variable and psi is also a variable, and we have relationship between I and psi is total flux linkage. In this question, the total flux linkage is represented by lambda. This is lambda. Okay, so we are first finding the total stored energy. This will be 0 to lambda, and I and lambda are related. What will be I? Lambda is equal to root under I divided by this air gap length is variable, so I will assume that instead of g I will write x. So I will be lambda square x square. Okay, so this will be lambda square x square d lambda. After integrating, we will get x square lambda cube divided by 3. Okay, so this is total stored energy in the field when the air gap is x. At air gap x, the total stored energy in the field is x square lambda cube divided by 3. Now the magnitude of force is differentiation of stored energy. So now we will differentiate it with respect to x. So magnitude of force will be 2x into lambda cube divided by 3. Now lambda is equal to root under I divided by x. So this will be 2x into I root I divided by x cube. So this will be 2 by 3 into I root I divided by x square. Now I is given as 2 ampere and the air gap length is given as 10 centimeter. This will be 2 by 3 into 2 into root 2, the value of current, divided by 0.1 into 0.1. This will be 188.5 Newton. To a delta connected induction motor, when rated voltage of 415 volt is applied, the line current is given as 120 ampere. When the rated voltage of 415 volt is applied to its stator winding, the stator windings are connected in delta fashion, and these are the line of supply. Here 415 volt is applied. Okay, now we have to find out the starting line current when a reduced voltage of 110 volt is applied. At 415 volt, the starting current is 120 ampere, and we have to find out the starting current at 110 volt. So in the single phase equivalent diagram of induction motor, we have stator reactance, this is Xm, this is rotor reactance, this is R2 divided by S, but in starting slip will be 1, so here we have R2. This is the single phase equivalent diagram of 3-phase induction motor, and this is single phase per phase voltage. So in case of delta connection, per phase voltage is equal to line voltage. So when you have applied 415 volt, okay, here you will have per phase current, there will be some current in phase. Okay, let's say this current is I, the per phase current is I. Okay, and in case of delta connection, the line current is equal to root 3 into phase current, and it is given as 120 ampere. Now if this voltage will be reduced in delta connection, when this voltage is reduced to 110 volt, so in this diagram voltage will be reduced to 110 volt. It is reduced from 415 volt to 110 volt. So in the same ratio, the starting current, the per phase starting current will decrease in the same ratio because voltage is decreased. So now the starting current will be, the starting phase current will be, let's say this is I2 phase, this will be 110 divided by 415 into the starting phase current for 415 volt. So now what will be the line current? This will be root 3 into phase current, this is root 3 into new phase current is 110 divided by 415 into I phase, and root 3 into I phase is nothing but 120 ampere, so this will be 120 into 110 divided by 450. This will be 31.8 ampere. This is a very easy question. In any machine or in induction motor, the starting current is directly proportional to voltage applied across the terminal. Okay, so if voltage so current will reduce in the same ratio in which voltage has been reduced. So initially current was 120 ampere, okay, and voltage is reduced from 415 volt to 110 volt. So new starting current will decrease in the same ratio. This will be 31.8 ampere. 100 by 200 volt two winding transformer is reconnected as an auto transformer such that its kVA rating is maximum. The connection has to be done in such a way that the kVA rating of the auto transformer should be maximum. So we have to find out that maximum kVA rating. So similar type of question was asked in set 1 also, and we have already solved that. So I will be quick here. The kVA in that solution, we observe that kVA will be maximum when connection is done in such a way that output voltage is summation of these two voltages. Output voltage has to be 300 volt and input has to be connected. Input should be connected. It should be connected on high voltage winding. Okay. This we observed while solving the similar type of question that was asked in set 1. So let's say we have this two winding transformer. This is 100 volt winding and this is 200 volt winding. kVA rating is 2 kVA. So for this winding, current rating will be 2000 divided by 100. Okay, this will be 20 ampere. This is 20 ampere winding and this will be 10 ampere winding. Okay, let's say this is the dot. Now connection has to be done in such a way that output voltage should be the summation of the voltage rating of the two windings, and we observed that how this can be done. When the negative terminal of first winding is connected to positive terminal of the second winding, or when positive terminal of first winding is connected to negative terminal of other winding. Let's say this is A, this is B, this is C, this is D. So in the output you will get summation of these two voltages when either A and D are connected or B and C are connected. So let us connect. In that question, in the question of set 1, we connected B and C. So let us connect, in this question, let us connect A and D. This is winding CD and here is the dot. We have to connect A and D, so bring it down and then connect with D. This is A and this is B, and here is the dot. So if on the dot you are taking positive, this dot also be positive. This is positive, this is negative. So this negative and positive are connected. So in the output you will get summation of these two voltages. This is 200 volt winding, this is 100 volt winding. Let's say you are taking output here. Okay. So from this negative to positive you will have gain of output. This is 200 volt winding, and for obtaining maximum kVA the input should be connected on high voltage winding. So where input should be connected? This is high voltage winding, so let us connect an input here. This is input and we have to find out the rating. So for rating, connect maximum input voltage 200 volt. So voltage across this winding is 200 volt, and these two windings are magnetically coupled. So the induced voltage in the secondary winding will be according to turn ratio. So if here voltage is 200 volt, voltage induced in this winding will be 100 volt. So from here to here you have gain of voltage V0, here to here drop of 200, here to here drop of 100. So this way we got output voltage as summation of voltage induced in these two windings. Okay. In the output, let us connect a load. Now to find out rating, we have to flow maximum current in the windings. So rating of this current is, high voltage winding is 10 ampere. So let us assume that 10 ampere current is entering in this dot. So 20 ampere current will leave from this dot. If current is entering in the dot of one winding, the current will leave from the dot of other winding. Okay. So 10 ampere will come through this winding. This is 10 ampere and this is 20 ampere. So here current will be 30 ampere. This current is 30 ampere. So input kVA will be input voltage into input current. 200 into 30, 6 kVA. Similarly, output kVA will be, this current is 20 ampere. So in the load 20 ampere current will enter, and voltage across load is 300. So this will be 300 into 20, again 6 kVA. Three single phase transformers are connected to form a delta star three phase transformer. We have a delta star three phase transformer, and voltage ratio is given as 110 volt by 110 kilovolt by 11 kilovolt. Okay. In three phase transformer, we have studied that this voltage ratio is line to line voltage ratio. Okay, it means here line to line voltage is 110 kilovolt. If on delta side line to line voltage is 110 kilovolt, then on the star side line to line voltage will be 11 kilovolt. This is not phase voltage ratio, this is line voltage ratio. The voltage ratio given in the rating is line to line voltage ratio. Okay, and this three phase transformer supply a particular load. Then we have to find out the ratio of phase current. Line to line voltage ratio is given, and we have to find out ratio of phase current, not line current. Okay, so in transformer we know that the ratio of phase current is inverse of ratio of the ratio of phase current or ratio of current is inverse of ratio of voltage. So if this is delta to star side voltage ratio, this is given as 110:11. This is voltage ratio, line to line voltage ratio. Line to line current ratio will be delta to star side, this will be 11:110. This will be line to line current ratio. Line to line current ratio, but we have to find out ratio of phase current in delta side to star side. So to find out ratio of phase current, let us first find out the ratio of phase voltages, and then we will take the inverse of that ratio of phase voltages. So to find out the ratio of phase voltages, in delta side, let us assume line to line voltage is 110 kilovolt. Then what will be the phase voltage? The phase voltage on delta side, in delta, line to line voltage is equal to phase voltage, so this will be 100 kilovolt only. And if line to line voltage is 110 kilovolt here, in a star side, according to line voltage ratio, on a star side line to line voltage will be 11 kilovolt. Then what will be the phase voltage on a star side? The phase voltage is 1 by root 3 times of line to line voltage. This will be 11 divided by root 3. Okay, so what is this voltage ratio? Delta to star, this is equal to 110 divided by, and this is ratio of which quantity? Phase voltage. Okay. This is 10 root 3 ratio 1. Okay, so delta to star side current ratio will be inverse of this ratio. This will be 1:1 by 10 root 3. Option A will be correct. It does not depend upon the which type of load is connected to the transformer. Okay, that's why I have not taken any quantity of the load. This will always be true. It does not matter which type of load or what amount of load is connected.